So in this little tutorial, what we're going to be doing is working an example of graphing a polynomial, going through all the steps. Now that we've learned all the different things that we need to look for, what we're going to graph is this function. F of x is equal to 1/5 x to the 4th minus 16 over 5th, 5x squared. Now, initially with the fractions, that looks intimidating, but not to worry. We will make it pretty. Remember, the highlights that we're looking for is, first of all, we want to find the vertex if it's a parabola. Second, we need to find the zeros. The zeros, aka x-intercepts. We also want to find the y-intercept. We want to take a gander at what the end behavior is so we can determine what's going to happen on either side of our graph. We need to determine what the symmetry is so we know what to expect, and also to save us a little bit of work possibly. Finally, we need to take a look at the multiplicity of the zeros. So we've got a number of different things that we need to figure out about this graph. So let's start up. First of all, the vertex is not a parabola. It's not a quadratic. So therefore, we don't even need to worry about one. We're done with that. Next up, we need to find the zeros. Those are the x-intercepts. What I'm going to do is to give myself a little bit of space. This is part 2. We're finding the zeros. We need to factor and find out what our zeros are. I'm going to rewrite it here since it's off the screen. F of x is equal to 1/5 x to the 4th minus 16 over 5 x squared. When we factor this out, first we need to pull out the greatest common factor. That's going to be 1/5 x squared. 1/5 x squared out of the first term is going to leave us with x squared. 1/5 x squared out of the second term is going to leave us with 16. Lo and behold, we have a difference of squares there. So we still have the 1/5 x squared, but over here we have x plus 4 and x minus 4. Okay, so that leaves us with our zeros. X is equal to 0 from the x squared. X is equal to -4, and x is equal to 4 from our two other factors. Okay, next up, we need to figure out our y-intercept. Our y-intercept is when x is equal to 0. So we plug in f of 0, we get 1/5 times 0 to the 4th minus 16/5 times 0 squared. This becomes 0 minus 0. So we have 0. So our y-intercept is at the origin. Next up, we need to figure out our end behavior. EB is end behavior for short. When we figure out the end behavior, we need to take a look at the leading term, and only the leading term. The leading term is 1/5 x to the 4th. 1/5 is positive, so therefore we are going to have a graph that is right side up. X to the 4th is going to give us a cup shape. When x approaches infinity, our function is going to approach infinity as well. When x approaches negative infinity, our function is still going to approach infinity. It's going to go up to the left and up to the right. So that gives us an idea of what our graph looks like on either side. Symmetry. I'm going to rewrite our function since it's out of sight. We don't want out of sight to be out of mind. X to the 4th minus 16 over 5x squared. We plug in negative x, see what we get. what we get is the same function. 1/5 x to the negative x to the fourth just becomes x to the fourth again. Minus 16 over 5, negative x squared just becomes x squared again because the negatives cancel out. This is even. Therefore, it's symmetric on the y-axis. Okay, finally, our last step is we need to take a look at our multiplicity of zeros. Not our last step, but the last piece of information that we are finding. We look back at our factored form. That is, there it is, right here. Switch colors for dramatic effect. Our factored form is right there. So we have a 0 of multiplicity 2 at x is equal to 0, and a 0 of multiplicity 1 at minus 4, multiplicity 1 at x is equal to 4. So, scrolling back down, we need to note that at x is equal to 0, multiplicity is 2. X is equal to both plus and minus 4. Both of them have a multiplicity of 1. Okay, so now we have figured out quite a bit of information about this graph without ever actually drawing it. So let's see what we've got. We want to make our axes pretty. If you can graph this on graph paper, please do so. It'll make your life a lot easier. You'll be able to actually see what you were doing. Okay, so first of all, what I'm going to do is I'm going to mark where my zeros are. X is equal to 0, x is equal to negative 4, x is equal to positive 4. Our end behavior, as we ascertain from the leading term, right here, we know on the left side of the graph, it's going to be shooting up. On the right side of the graph, it's going to be shooting up, both of them off into the sky. So we can expect that on either side, our graph is going to do something like this. Okay, with a multiplicity of our zeros, at x is equal to negative 4 and positive 4, our multiplicity is 1. That tells us that our graph is going to cross the x-axis. So here we're going to expect it to cross. Here we're going to expect it to cross the x-axis. However, at x is equal to 0, our multiplicity is 2. Therefore, we're going to expect it to bounce. Now, we know that through the intermediate value theorem, that in between x is equal to 0 right here and x is equal to negative 4, we do not have any other zeros. So therefore, it doesn't cross the x-axis again. We also know that it doesn't cross the x-axis between 0 here and negative, or at positive 4. So therefore, we know our graph is going to do something like that, but it's not actually going to cross the x-axis. Next up, we can graph our y-intercept. Normally, we would have a y-intercept, and many times it's not going to be at 0. In this case, it actually is at y is equal to 0. So therefore, when we plot our y-intercept, lo and behold, we've already got it. Here it is right here at the origin. So now we have quite a bit of information that we can use to figure this out. Now, last but not least, what we need to do is put together something that's going to give us an idea of the general shape here. So what I'm going to do is I'm going to do some test points. Remember from solving polynomial inequalities during first semester that what we need to do is we need to pick some test points that are over to the left of negative 4, in between negative 4 and 0, in between 4 and or 0 and 4, and then greater than negative, or greater than positive 4. So what I'm going to use is I'm going to use some easy numbers here. I'm going to use negative 5. I'm going to use negative 1. I'll use 1, and I'll use 5. I recommend that you use small numbers. They're easy to calculate. I also recommend that you plug it into the factored form of the equation. So our factored form, going back up, is this right here with the green arrow right next to it. So I'm going to rewrite that down here so that we can reuse it without having to scroll back and forth. It's f of x is equal to 1/5 x squared x plus 4 x minus 4. All right, first test point, let's do negative 5. F of negative 5 is going to be 1/5 times 25 times negative 5 plus 4, which is negative 1, times negative 5 minus 4, which is negative 9. As you can see, what we're going to get is a pretty big number. We've got those negatives cancel out. What we're left with is 1/5 times 25, which is 5, times 9. Maybe that number's not going to be so big after all. It's going to be 45. What I'll do to make this a little easier to deal with, we will plot these in gradients of 5. Better yet, let's do 10. 10, 20, 30, 40. Here's 45 right here. So when x is equal to negative 5, y is equal to 45. So negative 5, 45. Now, we have a couple of options here. One is we can do another test point when x is equal to 5. If I find f of 5, what will happen is that we'll have 1/5 times 25 times 5 plus 4, which is 9, times 5 minus 4, which is 1. 1/5 times 25 is 5, times 9 is 45. That's not a coincidence that those two numbers wind up being the same, because you may recall earlier on when we found the symmetry of this graph that it was symmetrical on the y-axis. So we would expect that if we had positive 5, it would have a y value of 45 as well. All right, nice convenient test point for between 0 and 4. I will use f of 1. That's going to be 1/5 times 1 squared, which is 1, times 1 plus 4, which is 5, times 1 minus 4, which is negative 3. That's going to give us 1/5 times 5, which is 1, times negative 3. F of 1 is negative 3. Now, since I've got a scale of 10 units on the y-axis for each tick mark, I'm going to have right around here. It's not going to be particularly large. So I'm going to draw a little arrow here, make it easier to see. This is 1, negative 3. Now we can calculate f of negative 1, but as we saw with f of negative 5 and f of 5, we actually don't need to. We can use the symmetry. So when x is equal to negative 1, y is equal to negative 3. Okay, so now we've got some test points. We know roughly what goes on. Now, finally, the coup de grace is to go ahead and connect the dots. Crossing that x-axis there, going through that point after bouncing off the x-axis, and going up and trying to make this as symmetrical as I can. Remember that this is a smooth curve. All polynomials make smooth curves. Well, let's see if we got something that is roughly approximating what we should have. Let's clear off all the other goodies that I've got on this calculator. And I'll go ahead and plug this in. I'll put it in factored form. 0.2, that's 1/5, times x squared forgot my parentheses, times x minus 4 times x plus 4. And what I'll do is now I have a rough idea what my window should be. So I will go from negative 10 to 10, that's fine. But my y, I don't think I need to go up to or go down to negative 4,000. I'll just go down to negative 20, say, shall we? And for my y maximum, I know I go at least to 45, so let's go ahead and go to 60. And when we graph it, there we go. As you can see, the graph is not perfect, but we have the highlights. Remember, we're watching Sports Center. We don't want to watch the whole game. All of these smaller aspects right around here, that exactly how low that graph goes, you do not have the tools to do that yet. You will learn how to do that in calculus. In order to find exactly where this local minimum is and this local minimum, you need to use something called a derivative, which you'll learn about in a couple of years. For right now, this kind of graph will suffice.